Okay, everyone, it looks like it's about 7 o'clock, so let's get things kicked off. So some of you may have been around for the talk on Monday, which was about reverse engineering. In that, we kind of just went over some basic stuff that I want to review today. A lot of that was just to kind of make sure that everyone was on the same page, though, because reverse engineering is one of those topics that requires a little bit of a background knowledge. So if you've taken comp.org, if you've taken data structures, if you've spent a little bit of time in the CS curriculum, you're probably set in that regard. But if not, we have an INTROSEC video, which I think does a decent job of trying to introduce the very basic concepts. And if you weren't able to make it to that meeting, then we'll just kind of breeze through, give everyone a quick refresher, and hopefully make sure that everyone is on the same page for this talk. So we'll be starting off reviewing some of those topics, and then we'll be diving into some new things, namely static and dynamic analysis, because on Monday, for INTROSEC, we spent some time kind of talking about the theory of reverse engineering and talking about like how in theory these programs work. But the topic for today is we want to get a little bit more hands-on. We want to actually give you some hands-on experience and show you how this works in practice, which is very exciting. So one of the things that we talked about on Monday was kind of the memory map of a program. So where different pieces of information get mapped into the memory of your computer. And one of the big points that we made that is going to come up over and over again, especially in the next couple of weeks, is that code and data both live in memory. So the stack is storing these local variables. So if you have a function and you have a variable I, within that function, that's going to be stored in the stack. It also stores some really interesting and exciting function metadata. So we talked a little bit about how when you call a function, the computer needs to know where to return to. And so the way that it does that is it takes the address that it was called at, and it just pushes that onto the stack. So the stack is going to store things like return addresses, it's going to store saved base pointers, and it's also going to store local variables. The heap we didn't talk about as much last time. If you've taken data structures, you're probably all too familiar with the heap by now. But that's where a lot of the bigger data that you can't store on the stack because it's too large or you don't know the size of it is, as well as like data that has a longer lifetime, so data that you don't want going out of scope when you exit a function. And for the context of this talk in the next couple of weeks, you probably don't need to care too terribly much about the heap, but there are some interesting properties of the heap that make it really cool from a like an exploitation standpoint. And the last thing that I wanted to really reiterate is that memory is kind of slow compared to a lot of the other storage devices that we have access to when we're running a program. And so namely, when I say that, I'm referring to registers, which are really, really fast, but they're also really, really tiny. And because they're so fast, when a compiler compiles your program, it's going to try to figure out how to arrange it in such a way that it uses these registers as much as it possibly can, and it doesn't spend a lot of time waiting to write things or read things from memory. So we talked about a lot of different registers on Monday. The important ones I've tried to list here, or at least most of the important ones. And because we are mostly focusing on 32-bit systems, just because I think that is a little bit simpler, I've listed the 32-bit versions of these. So they start with an E. If we're dealing with 64-bit systems, a lot of this is exactly the same, but the registers are going to start with an R. And the registers are going to be twice as long. They're going to be 64 bits long, so 8 bytes instead of 4 bytes, or 32 bits long. And so the first 4 of these registers, that EAX, EBX, ECX, and EDX, those are all what's called general purpose registers. And so when you run your program and it needs to just store a piece of data, like in a scratch space essentially, it's going to use these registers. The next 2 kind of define the stack and the frame of the stack, so the stack frame, which your function is going to be accessing. So ESP is the stack pointer, and that's going to point to the top of the stack. Last week we spent a lot of time arguing about how what the top of that stack should look like and how the stack should be drawn. But that's basically just going to point to the next element to be popped off, or where the next element will be pushed onto, which is all that really matters at the end of the day. And then the base pointer points to the base of that stack frame. So that's going to kind of point to the bottom. You can think of it. The ESP is going to point to the top, the stack pointer is going to point to the top, and then the base pointer is going to point to the base, or the bottom. And the last register that we really want to make sure everyone has a strong understanding of is the instruction pointer. So on a 32-bit system, that's going to be EIP. And that points to the address of the instruction that we're currently running, because if we remember, program code is loaded into memory, so every instruction is going to have an address associated with it. And that kind of ties in nicely to the next topic I want to make sure we review a little bit, which is assembly. So if you've taken Comporg, you're probably familiar with MIPS assembly. A lot of that same, or a lot of those same concepts apply really nicely to x86, which is the architecture that we're going to be focusing on, just because that's what most desktops and laptops and PCs are going to be running these days. And there are a ton of instructions in assembly. There are, I can't remember the exact statistics, but it's easily many thousands, probably tens of thousands of instructions on a modern system, and you don't need to know all of those. There are a couple of common ones that you probably should know, and we've kind of broken those up into 5 different groups here. So there's arithmetic instructions, so that's things like add, or subtract, or multiply, divide, XORing, things like that. A lot of bitwise arithmetic fits in there. So exclusive or XOR, you've got AND, etc. And again, if you've taken Comporg or the equivalent, I'm sure you're very familiar with what that bitwise arithmetic will look like. And if you haven't, that's totally fine as well. It's honestly not as complicated as it sounds. The next category of instructions that we want to talk about are jumps. And those basically take the instruction pointer and they jump to somewhere else. They redirect that execution, and they just send it to point somewhere else at a different instruction. Some of those jumps just happen unconditionally, so those jumps will happen no matter what. They'll always redirect execution. And some of them happen conditionally. So maybe if 2 variables are equal, if 2 values are equal, or if one value is greater than the other value, then a jump will take place. And the way that you compare those values is with what's called a test instruction. And so that's going to compare values, and it's going to set some special flags, which we didn't talk about in the registers section, but you can kind of think of those as registers as well. And then last but not, or I guess not last yet, but the next category is kind of memory access. And we focused mainly on ways that you can access or modify the current stack. And so that's mainly going to be referring to pushing and popping instructions. And those, as the name would imply, if you're familiar with a stack data structure, just push onto the top and pop off of the top. And then there are many other ways that you can modify memory as well, but we're not going to be going into too much depth on those just yet. And then the last category of functions is calls, which the name is fairly self-explanatory. There's a call instruction that allows you to call other functions and to execute other functions. So that kind of is a very, very brief 10-minute overview of what we spent about 45 minutes talking about on Monday. So if you saw that talk on Monday, or if you took Comporg, should be set nice and fresh in your mind. If you didn't, that's totally fine as well. The lectures are, the talks, the meetings, I guess I should say, are recorded on our YouTube channel, so you can go back and watch those as you please. So now that we've kind of reviewed a little bit about how a program gets executed, I want to talk a little bit about how we can use this knowledge to figure out what a program is doing, and we can use this knowledge to reverse engineer a program. And so there's two main ways of doing that. The first is static analysis, which is where you execute this program statically or without running it. And then the other way is dynamic analysis, where you run it and you have a little bit more context about the program because you're running it, so you can examine the stack instead of having to try to think about it really hard and think about, like, oh, what gets pushed here, what gets popped here. And so that's really useful as well. But first of all, we're going to be talking about static analysis. On Monday, we spent a little bit of time looking at assembly. If you've taken CompOrg, I'm sure you've looked at assembly as well. It probably looked a little bit different than this because it was MIPS instead of x86. But we spent a lot of time kind of walking through this line by line and saying, okay, this is what this instruction does, this is what this instruction does. It's jumping here, where does it jump to, etc. And we also mentioned a couple of slides ago that assembly is almost what the CPU sees. It's almost exactly what the CPU executes. And the reason why I say it's almost is because the CPU doesn't know what, for example, a move instruction does. It doesn't know what, like, a jump instruction does. It knows what, like, the bytes EBFE mean, but it doesn't know what, like, jump -1 means or something like that. It only understands the bytes. It doesn't understand assembly. However, as a human, it's really, really hard for us to understand the bytes, but it's, well, I wouldn't say easy, but easier for us to understand the assembly. And so a disassembler, as the name would imply, it takes these bytes, it takes this raw data, this raw binary, and it lifts it up into assembly, which is a lot easier for us to understand and look at. And then a really useful abstraction, kind of just like how taking this these bytes and converting them into kind of more human-readable assembly is an abstraction that makes it a little bit easier for us to understand. Another really powerful tool is what's called the control flow graph. So this is talked about, like, very, very briefly in Principles of Software, if you've taken that class. I think it's also mentioned in, like, one class in CompOrg. But basically, what a control flow graph does is it graphs out how, like, the different paths of execution within a program. And so on the left, we have the assembly that we're used to looking at here, where we have a bunch of pushes, etc. And then we get to a JLE instruction here, a jump less than or equal instruction. But because this is all one linear mass of instructions, it's really hard for us to look at this as a human and say, okay, where does this jump to? And we track down the address, and we find the address, and then we can start reading from there. However, a control flow graph is a more graphical way of looking at that, where we can say, here, there's a JLE instruction, and if it's less than or equal to it, it jumps all the way down here. If not, it jumps to this block of code instead. And so that makes it really easy to analyze conditionals like that, so if-else statements, essentially. And it also makes it really easy for us to visually recognize certain patterns. So, for example, if you look here, you have one block that jumps all the way up here, and then there's a path back down to this. And so we can see this looks like a loop. This looks like some kind of for loop. And then if we look in this basic block, as it's called, this node in that control flow graph, we're going to be incrementing a variable and then doing some other computation. So just looking at this, we can see, okay, there's a good chance that that's something like a for loop. Whereas if we look at this this pile of instructions in a linear view, that's much harder to recognize. And so this control flow graph is a very useful abstraction that just gives us a little bit more metadata, so to speak, about a program, and it gives us a little bit more intuition about how it works. And kind of along that same train of thought, we have all of these different abstractions, and we have this pipeline, essentially, into like lifting things into higher and higher level abstractions that are further from what the computer sees, but easier for us as humans to see. And so kind of the crowning jewel there is what's called a decompiler. And as the name would imply, a decompiler kind of does the opposite of what a compiler does. So instead of taking source code and converting it into this raw stream of bytes, this binary, that a CPU can execute, it takes this binary, this stream of bytes, and it lifts it up into almost pseudocode that's a lot easier for us as humans to see and to understand. So we can actually see this control flow graph on the left. We can gain a little bit of information about it. We can see here, it looks like this is another kind of loop of some sort. And then there's a bunch of logic. There's a bunch of like branching conditionals here. But if we look on the right at the decompiled code here, at the higher level abstraction, it's a lot easier for us to see, okay, it does some stuff, and then there's a while loop. And for us to look at these conditions and see in a much nicer format, oh, it's comparing this value, a signed comparison, to 7. And so that makes our job as reverse engineers much, much easier. And that kind of begs the question, like, okay, if these decompilers exist, why did we just spend a bunch of time talking about assembly and talking about stacks and talking about how things work at a low level, when turns out there are these tools that just kind of interpret all that information for you? They just kind of lift these binaries into pseudocode, into human readable code. And the reason for that is because it actually really is important to understand assembly for cases when a decompiler doesn't work, which unfortunately is much more common than I would like. And the reason for that is because a disassembler is a very close mapping to what the CPU sees. So a disassembler is effectively just representing what the CPU knows about a program, whereas a decompiler is trying to represent what the programmer knew when they had this source code and they compiled it. And that's really, really difficult because a lot of information is lost when that code is compiled. So if you have a function named foo and you compile it, unless you compile it with a special flag, that name is going to be lost. If you're trying to reverse engineer that, you're going to see some garbled mess, and it's not going to be foo. It's going to be like sub 123 or something like that. It's going to be a much less readable or understandable name. And that obviously applies to variable names as well. So if you have a for loop and you have a counter named I, well, that's not going to be named I anymore when we're looking at it in a decompiler. And then another much bigger issue is actually with the types of different variables. So, for example, if you compile this program, if you compile a program that uses a pointer, oftentimes a decompiler won't know if that's a pointer or if that's an integer or if that's some other data type entirely. And if it is a pointer, it has no idea what it's pointing to. And so using a decompiler is definitely useful in many circumstances, but it's very easy to become over-reliant on it. And then in some special circumstances, when we're looking at malware or when we're looking at code that the authors really don't want us to be looking at, there are a lot of special tricks that can be used to fool a decompiler. But because a disassembler is much closer to what the CPU sees at execution, it's really, really difficult to trick a disassembler, but it's relatively easy to trick a decompiler. So it is very important, even though there are these tools out there, to understand how assembly works, so that when they fail, you understand why it failed, and you have the tools in your belt to be able to kind of go in and reverse engineer that function or that program anyways. And so with that in mind, I want to show a quick little demo of a program that I wrote earlier today that we can step through or we can examine in Ghidra. Ghidra is a very common, very popular tool for reverse engineering. It's what I recommend for anyone who's just getting started right now because it's totally free, and it even has this really cool decompiler built in. This wasn't available to the public until quite recently. This was actually published last year by the NSA, and before that, the only way that you could have a decompiler was if you basically sold a kidney to get access to another product called IDA Pro, or if you worked in a very secretive industry and you were using this for work at a place like the NSA, or I'm sure other places have developed their own internal tooling. But yeah, anyways, Ghidra is a really powerful tool, and as we see here, it kind of automatically is able to figure out what the entry point for this program is, what the starting point is. And we can see here there's a main function, so we can click on that. We can also navigate to main in this functions listing. I think by default it's on the left here, but I've just moved it down to the bottom because I think that that's a little bit easier to read. We can see inside of main, we have a couple of things here. We have a character buffer with an input, and we have a password buffer. So we can kind of look at this, and we can see it prompts for a password. It gets OX 11 bytes, puts that into an input buffer. This is a funny way of stripping a new line, and then it calls this generate password function before comparing them. And we can see in that generate password function, this is some pretty simple logic that just takes in this this character array. It sets the first character to an F, LAG, and then a starting bracket, and the last byte, well, the last byte is a null byte. It's a terminator to that string, but the byte before that is going to be a closing curly bracket, and everything in between those bytes is going to be generated by taking the current index here in this, effectively this for loop, and doing exclusive OR with the previous byte in that password before doing a bitwise AND, so basically just masking it down to OX7A, which I believe is going to be the lowercase z, which is right at the right near the upper bound of the printable characters. So it's going to do some of this arithmetic, and then it's going to generate a password that way to compare things to. And if this was a normal semester, I would be standing up at the front of the lecture hall, and I could like walk through re-implementing this code with you all live. However, one of the many unforeseen difficulties of this current pandemic is that I have an incredibly loud keyboard, as you have probably picked up on. And so I'm not going to do that to all of you. I'm not going to make you suffer through that. I'm not going to injure your eardrums while I try to implement this live. And so instead, I've just gone through and I've re-implemented a lot of that exact same code in Python, which is a really common technique when you're trying to reverse engineer things. You often try to kind of rewrite them in a higher level language like Python so that it's easier for you to understand what's going on. So this is going to do the same thing. It's going to set those bytes that we know the concrete values for, and then all of the bytes in between, it's going to get the numerical value of the previous byte, XOR that with the current index in the string, and then do a bitwise AND with OX7A, which was that magic value we saw before that corresponds to the upper range of the printable ASCII characters, the printable characters, before converting that back into a letter and putting that into the password array. So it's fairly straightforward. Let me see if I can run that for you really quickly. And we can see that this is going to spit out this interesting looking string. So we can run the demo, and we can paste that in, and we can see this does in fact match the generated password. And so that's going to tell us access granted instead of that access denied message. So that's a really, really quick walkthrough of a fairly simple program to reverse engineer. If you haven't tried Fair Game yet, I highly recommend you try to step through and you kind of try to follow that same thought process, where you can look for functions that do computation like that, and you can kind of try to re-implement a lot of that computation in a language that you're more familiar with, like Python. And I think that's going to get you a really long ways in the Fair Game competition and in a lot of CTFs in general, really. That being said, I do want to show you guys another way to tackle this problem, and that is dynamic analysis. So if you've taken data structures, I know at least when I took it, there was a lab and a homework specifically about using a debugger. And specifically we were using the GNU debugger, or GDB, because that's kind of built into a lot of Linux distributions, and a lot of the CS curriculum, at least here at RPI, I assume at many other schools as well, is built around Linux because it's open source and it's very easy for us to find information about. So on the left here, you can kind of see a stock GDB run. So you open it up, it prints some information, you try to set a breakpoint, which we'll talk a little bit more about later. You run it, and then you hit that breakpoint, and it just kind of spits you into an interactive prompt. And that works, that's fine. However, it's definitely not ideal. It's definitely not easy to parse a lot of information out of, and you kind of need to know what you're doing to be able to get a lot of use out of GDB. And so a lot of people have developed plugins for GDB, and one of those plugins that I highly recommend is something called Jeff, or the GDB exploitation framework. And on the right, we can kind of see the same run happening in Jeff, where when we hit that breakpoint, it's going to display a lot of useful information. So we talked about registers before. This is going to just dump a bunch of useful registers. It's going to show us the value of these registers. It's going to show us what's on the stack. So we talked about pushing and popping before. This is going to show us if the next instruction, or actually this instruction right here, very conveniently, is a push instruction. So we can see that the value in RBP, which we can look up here, is about to be pushed onto the stack. And we can see the stack as it is. We can see RBP. It's incredibly useful, and we can even see the instructions that we have executed, that we are executing, and that we are about to execute. So when you are debugging at the assembly level, GDB works, but it works a whole lot better if you're able to kind of complement it with something like Jeff, which is a plugin specifically designed for people that are working at a low level in GDB. And so we talked about Jeff, and we talked about some of the features. So we talked about that context menu. It also has a lot of useful information. We talked about, or I alluded to some interesting heap properties before, and how the heap can be a really interesting topic when it comes to exploitation, when it comes to especially in CTFs, the pwn category. And then it also has a lot of really useful tools built in to display exploit mitigations, and we'll be talking a lot about those in the coming weeks. So if you're using the tools VM, we have installed Jeff already on the tools VM, so you should be good to go just out of the box already. If you aren't using the tools VM, that's also completely fine. Jeff is very easy to set up and to install on your own as well. So we've talked a lot about a debugger, and we've talked about how useful a debugger is. However, the fact remains that a debugger is kind of difficult to use if you don't have a certain baseline knowledge, if you don't know these commands, because it is this textual interface. Like, you don't have a nice graphical way of displaying information and options and stuff like that with GDB. So there are a million different commands. Like, we talked about how there's an ungodly number of instructions in x86. There's also a ton of instructions in GDB, especially if you're using an extension like Jeff. But for the most part, the ones that you really need to know how to do are listed on this slide here. So obviously, when you're debugging a program, it kind of helps to be able to run that program, to start that program's execution. And there's two really useful but subtly different commands in GDB to do that. There's R, which is run, and then there's also S, or start, which tells GDB to start that execution, or to start that program, and then it pauses. It sets a breakpoint on main. And speaking of breakpoints, a breakpoint you can set with either the B or breakpoint instruction. I forgot to put that on the slide, and I'm sorry about that. But that's basically going to tell the debugger to pause when it hits that address. And once you hit that address, then a lot of the fun really begins. That's where a lot of the power of a debugger really comes in. You can continue, so you can just kind of resume execution as if nothing had happened. You can just keep going. And you can also step through instruction by instruction. So you can do that with the S command, that step, or a next, N, or you can do like SI, NI, etc. That's just a way that you can step one instruction at a time. And so you can really see exactly what's going on. When you step through instruction by instruction and you pair that with the really useful context menu in these plugins, because you can see the value of every instruction. You can see how the stack changes at every instruction. And that's incredibly powerful. And then you have like a finish command, and that will basically run and execute all the way up until when the function returns. So if you're waist deep in a function and you just want to get out of there and get back to the function you were debugging before, the fin command, the finish command, is a great way to do that. And then finally you have the quit command, which will just exit GDB. It'll end your debugging session. And you have Control-C, which kind of sends an interrupt, so it's going to pause as well. That's really useful if you need to be able to like see what's happening under the hood or access something like that. You don't you probably won't be using that as much. So just like we demoed the static analysis approach here, I want to give a quick demo of how you could do this in GDB as well. Because we can see from the source code, if I step back to main, we generate a password, we put that in a static, in a password buffer here, and then we just do like a comparison here. And so we can go through all of the effort of reverse engineering this generate password function, and then re-implementing it in Python so that we can generate that for ourselves. Or we can just as easily, or in fact much easier, I would argue, go into GDB, and we can set a breakpoint for that address, which we can extract very easily in Ghidra. Basically just want to look for where that stir and compare function gets called. You can look up that address, and we should probably copy the whole thing. We can copy that over, and then if you have taken data structures and you're familiar with what a pointer is, that star command is basically doing the same thing. It's basically dereferencing. So you're setting a breakpoint on that instruction. So we set a breakpoint, and then we run. We can just enter some random password here. So we have, we can see, because I did compile this with symbols, we get a little bit of extra information here, where we can see the exact line in the source code that this lines up to. And we can see here, we're on string compare. We have an input argument, we have a password argument, and we have a password length that's going to tell it how many bytes to compare. And we can see this plugin is actually really powerful. This is smart enough to be able to look and introspect and figure out exactly what these values are. So it knows we entered ASDF for the input there for the password prompt, and we can see that by setting a breakpoint here, we can actually examine the memory, and we can actually see exactly what is in that variable as well. And if we didn't have symbols, we could also just look up the address of this, or the where this password is stored in memory. And we do something like x/s, so examine as a string, and then whatever address it is. I didn't know the address off the top of my head, so I just did the symbol, but you can do it with an address as well, which you can extract very easily from a tool like Ghidra. So that's kind of it for today. We walked through a quick review of what we covered on Monday with some basic concepts of how a program gets executed, and then we leverage those principles to talk about how you can walk through a program statically, and you can figure out statically what it does, and then also how you can do so dynamically, which gives you a little bit more information as well. So that's all I want to talk about for today. If you tune in next week, we'll be talking about how you can leverage these skills that you learned today and on Monday to actually change what a program does and to actually exploit vulnerabilities in it. So I hope to see you next week.